Hi everyone. In this video I want to cover the method of integration by substitution, which is a method that will allow us to solve some integrals that are a little bit more complicated and we can't see the antiderivative right away. So first I will cover the case of definite integrals. So those are integrals where the bounds of the integrals are part of the problem. And then I'll cover the case of indefinite integrals separately. All right, so let's start with definite integrals. So let's work. I'm just going to work through a few examples and explain how the method works through examples. All right, so in example one, I just want you to compute um, the integral from 0 to 4 of 2x times square root of x squared plus 9 dx. Okay, so that's it. In order to compute this integral, so it's kind of hard to figure out what is the antiderivative of this function, right? The function in here is what we call the integrand. It's kind of hard to come up with an antiderivative for it. Maybe if you're really familiar with the chain rule, you can kind of see what you need to make happen here to find the antiderivative. But the method of substitution lets you just solve this pretty simply and also more complicated integrals. I want to start with a simpler one. Okay, so when are you going to use this method? So the idea here is that you have, well, let me rewrite the integral. So integral from 0 to 4 to x squared plus 9 square root dx. So basically you're going to use this method. You have to look at your integral, and if you see a complicated function like the square root of x squared plus 9, that's kind of complicated. And you see an expression here like x squared plus 9, and you see its derivative as well, right? So this expression, x squared plus 9, the derivative of x squared plus 9 is 2x, right? And you're seeing 2x here, right? So when you're in a situation like this where you see a function and its derivative inside of this integral, you have a good chance of applying the substitution method and getting somewhere. Okay, so what we're going to do is we're going to call x squared plus 9 a new name. So usually the variable we use is u. So we call this method as well, we call it u substitution. So it's very common to denote the new variable by u. And so x squared plus 9 is equal to u. And to see how to proceed here, what you do first is compute the derivative of u. So du dx. Right, so the derivative of u with respect to x now is 2x. It's good to use this notation here because it's going to make it a little prettier when we work out the integral. And so what you do is you here multiply by dx on both sides. It's not totally legal mathematically, but it's okay. And it lets you know how to apply this method. Right? So du then is 2x dx. And so you see here you have this 2x and this dx together. They are going to turn into a du. Right? And this square root of x squared plus 9 is going to turn into a square root of u. Right? So what this method is going to do is going to turn our integral in the x variable into an integral in the u variable. This square root of x squared plus 9, as I said, will turn into square root of u, and 2x dx by this formula will turn into du. But we still have to take care of what the bounds of the integral is, what the bounds are, right? So the original bounds are from 0 to 4, and they're going to change because you change the variables, right? So I like to write it like this. The original bounds, the variable x was ranging from 0 to 2. Oh, sorry, 0 to 4. Now the new variable u is going to range between new values, And all you have to do is take the original bounds and plug it into your formula here to see what the u is going to turn into. Right? So when x is equal to 0, plugging into x squared plus 9, you get 0 squared plus 9, and you get a value of 9 for u. Right? So u will range from 9 because x was starting at 0. And then for the value 4, you get 4 squared plus 9, which is 16, plus 9, which is 25, right? So that's the top of the integral now. So you can box here your u sub. This integral then will be from 9 to 25. Okay, and now you have this integral in u. You can just solve how you would usually solve. But the good thing about this u substitution is it simplifies the integral quite a bit, right? So the square root of u, we can find the antiderivative using the power rule here. This is the integral from 9 to 25 of u to the 1/2, right? A square root is the same as raising it to a half. And if you want to use the power rule, right, so this is going to turn into u to the 1/2 plus 1, right? You add 1 to the exponent and you divide by 1/2 plus 1. And this is for u equals 25, u equals 9. Okay, so you can rewrite this a little bit more. 1/2 plus 1 is 3/2, right? So this is u to the 3/2. And here you're going to divide by 3/2. But instead of having a double fraction here, dividing by 3/2 is the same as multiplying by 2/3. So that's what we get for u equals 25, u equals 9. Right, so evaluating this, we first evaluate u equals 25 in here. So you're going to get 2/3 times 25 to the 3/2, right? And then minus the bottom bound, which is 2/3 9 to the 3/2, right? So this is 25 3/2. You can first evaluate the 1/2. I'll write it down. So this is 2/3 25 to the 1/2 cubed, right? Minus 2/3 9 to the 1/2 cubed. You can do it in parts like this. The exponents multiply. It's the same thing. But 25 to the 1/2, that's square root of 25, which is 5, right? So this is 2/3 times 5 cubed minus 2/3, and square root of 9 is 3. So this is 3 cubed. Okay, so 5 cubed, 5 squared is 25. 25 times 5 is 125. So this is 125 times 2, which is 250. 3 squared is 9, and 9 times 3 is 27. Times 2, you're going to get 54. So minus 54/3. I'm at the end of the page. This is 196/3. Right? That's right. And I don't think 3 divides this. So that's it. That's the end of the integral. Right? I like to do that. And I'm done with the problem. Okay, so hopefully it made sense. We started with an integral in x. We saw a complicated expression here, but we saw that the derivative of that expression also showed up in the integral, and so we were able to use this substitution to evaluate the integral. Yeah, went through these steps. Okay, so let's do one more example of one more definite integral. So example 2. Compute. So let's do the integral from 0 to the 4th root of pi/2. It's kind of an odd number, but a weird number, I mean. And then here I'm going to do x cubed sine of x to the fourth dx. Okay, let me write it over here again. So integral from 0 to the fourth root of pi over 2 x cubed sine x to the 4 dx. Okay, so we want to compute this integral. I'm going to do my u sub over here this time. I think it looks better. All right, so you look at this integral. It's kind of tricky. You might be able to find the antiderivative in your head again because it's a simpler example, but I want to use it to illustrate our method. You have this complicated expression, sine of x to the 4. That's pretty complicated. But then you see here in x to the 4, the derivative is 4x cubed, right, from the power rule. And you see it in x cubed here. You're missing a 4, but that's not a huge deal because it's just a number, and the numbers won't really bother us very much. But x cubed, that's basically the derivative of x to the 4, and so it's a good idea to use u sub or a substitution for this integral. So we're going to go ahead and call u equals x to the 4. So then du dx is equal to 4x cubed. Okay, and so multiplying by dx on both sides, and I'm going to also divide by 4 on both sides, you get the du over 4, right, dividing by 4, is equal to x cubed dx. Okay? So if we use these identities here, this is going to be equal to the integral. Now sine of x to the 4 will become sine of u, right? Because x to the 4th is u. And x cubed times dx, that's equal to du over 4, right? Right? So this number can come out of the integral here. We're basically just left with an integral of sine, which is pretty easy to solve, right? But we still need to pay attention to the bounds here, okay? So our bounds are ranging from 0 to fourth root of pi over 2. So our variable u is going to range from, so what you're going to do, you're going to take, to figure out the lower bound, you take x equals 0 and you plug into your formula for u, right? So you're going to get 0 to the 4, right, which is 0. So that's the lower bound for u. Now the upper bound is you're going to take the fourth root of pi over 2 and plug it into your formula for u here. So you're going to get the fourth root of pi over 2, and then that to the 4, right? Because you're going to plug into this x to the 4 here. But then these will cancel out, right? This is a pi over 2 to the 1 over 4 to the 4. That's just pi over 2, right? So that's the upper bound for the variable u. Okay, so our u sub is right here. You can box it. I generally like to box it like this. And I would also, when I'm writing an assignment, I would probably erase the scratch work here. But I'm going to leave it so you can see what we did, right? Okay, so the bounds in the u variable here are 0 to pi over 2. All right? And so how to solve this integral? Well, you just need an antiderivative. Let me take the 1 over 4 out. You need an antiderivative of sine. So you know the derivative of sine is cosine. Derivative of cosine is negative sine, right? So to get a sine here, you can just get a negative cosine u in there. Derivative of negative cosine u is negative sine, which is sine. So this is for u equals 0 to u equals pi over 2. Plugging it in, you get 1 over 4 minus cosine of pi over 2 minus the lower bound, which is negative cosine of 0. Okay? Right, so you take the upper bound, you plug into negative cosine, you get this. Then minus, you take the lower bound and you plug into negative cosine, you get that, right? So there's a double negative here, you have to be careful. But, so cosine of pi over 2, that I'm going to want you to know how to do these things. So I'm going to scratch work for you here. You can use the unit circle to figure it out. So in the unit circle, the x-coordinate is the given an angle theta, right? The x-coordinate is cosine of theta, and the y-coordinate is sine of theta. So pi over 2, so let's see. So if you want pi over 2, that's 90 degrees. So it's this point right here. This point has coordinates x-coordinate 0 and y-coordinate 1. And so if you want cosine of pi over 2, that's the x-coordinate, which is 0. So this is 0. Right? It's the x-coordinate of the point with angle 90 degrees of pi over 2. So this is 1 over 4 minus 0 minus negative. What is cosine of 0? When the angle is 0, so let me use a different color here. Okay, I'll use this. For the angle 0, theta equals 0. Okay? So let me see, theta equals 0. You have this point right here. This point has coordinates 1, 0. Right? This is the unit circle, so the radius is 1. X coordinate is 1. Y coordinate is 0. So if you want the cosine of this angle, is the first coordinate. It's 1. Okay? So cosine of 0 then is 1. All right, so this is 0 minus 1, which is 1. It's just 1 over 4. That's it for this integral. Well, that 4 is almost looking like a 9. Let me write it again. 1 over 4. Okay, to make this the same, let me call this. All right, so we started with this integral in x. We made a substitution u equals x to the 4 because we saw the derivative of x to the 4 outside here, x cubed, right? So doing that, this turned into a sine of u, x cubed dx turned into a du over 4, and we changed the bounds. And then we just found the antiderivative of sine, which is negative cosine, plugged in the bounds there. Then we had to evaluate this cosine of pi over 2 and cosine of 0, which you can do by using the unit circle to remember how to find these things. Got that the value of the integral was 1 over 4. So I'll stop this video here, and in the next video, we're going to cover indefinite integrals. Okay? See you soon.